It's often taught in a way. I have loads of students who come to me and find vectors really hard, and so hopefully I'm going to be able to make it simpler for loads of you today. Yeah, so this is kind of aimed at ages like 13, 17, people coming back to school. The big catch-up that we're running this week has got loads of different subjects. There's still more maths, biology, chemistry to come over the next few days, although the English and the philosophy and the geography and all that kind of stuff has now happened. But yeah, if you are joining for the first time, then know that you can ask questions at any time you like by dropping them into the chat, and you can interact and throw your answers my way when I ask you questions, and you can ask me questions, and it'll be great. So let's get started. I first wanted to start with this ant. This is actually just a random ant that I found, but I wanted to know what you guys thought. If you dropped an ant out of an aeroplane, then would the ant, in fact, let's not do an aeroplane. Let's say you're dropping the ant off the top of a tall building, dropping it off the top of the tower of the Palace of Westminster, which people often call Big Ben because of the bell inside it, but it's not called Big Ben. Might be called the Elizabeth Tower actually now. Anyway, big clock tower, you drop an ant off the top. Is the ant going to survive or not? Will the ant be fine falling off the top of a clock tower? What do you think? How is the ant going to feel about being thrown off the top of the clock tower? And Queen's saying yes, the ant will be fine. That's true, the ant will be fine. Why? Why will the ant be fine falling off the top of a clock tower? What crazy advantage does the ant have over us when it falls off the top of a huge height? Why is the ant going to be fine? Why a survivor? Now, while you guys are telling me why you think an ant would be fine if it fell off the top of a tall building, I just want to tell you how the fastest ant in the world, or the fastest ant that we know about, is something called the Saharan silver ant. It's not this one. It's a silvery ant. It's all a bit of silver, so it can be like the Saharan silver ant. The Saharan silver ant can run so fast that if a human could run at the same speed relative to its size, then we could complete 100 meters in less than a second. We could run 100 meters in under a second. So how fast do you think the Saharan silver ant can go? That's my other question to you, which is also totally unrelated to vectors, but I just thought it'd be fun to start off with some ant-based knowledge before we go into the bit about vectors. So, any ideas? Yeah, okay, so why a survivor? The reason is because the ant hits terminal velocity. So what that means is that the ant has so much air resistance compared to its tiny weight that it'll have all this force of air pushing upwards against it compared to the small amount of weight pushing downwards. And so it actually will only be able to accelerate up to quite a low speed, and then it'll just kind of drift down to the earth at quite a low speed. And it would be ideal if humans had this kind of air resistance, because then we could fall off anything. But in order to give us that much air resistance, we need some big parachutes to slow us down. Otherwise, our fate will not be so good as the ant. But yeah, so the top speed of a Saharan silver ant is 85.5 centimeters every second. 85.5, it can go almost a meter in a second, just this tiny little ant. Unbelievable. Anyway, right, let's get on with vectors and maths. So let's go down here. So first of all, what is a vector? Let me get rid of this stuff at the top. So a vector is kind of, so a lot of things in the world you just measure with numbers. Like, for example, if we were going to measure the weight of my jumper, then we would measure it as being like, I don't know, 1 kilogram or something like that. I don't know. But yeah, so we measure it and it's just a number. And in the same way, things like time, it's just a number. Like, as the amount of time goes past, it's just a number. But some things that we measure in the world, a number isn't enough. Some things that we measure in the world, we also need to know a direction. And these things are called vectors. So, for example, if you were just like stood on the ground and someone pushed you from one direction, or maybe if you were pushed from one direction, then you would need to know the direction of the force for it to make sense. So if someone is going to push you with a certain force, then it only makes sense with a direction. And so we describe this as being a vector. A vector is something that has a size and a direction. It's got a size and it has a direction. Now, in maths, in order to describe a vector, what we do is we just draw an arrow. We just draw an arrow that's going in the direction. Let me get rid of this person here so that we can draw an arrow. We just draw an arrow that's going in the direction of the vector. So let's say a vector could be something that's just like a force, for example, going in this direction. Like, let's say you're pushing your trolley in the supermarket towards the sugar snap peas to buy the sugar snap peas because the sugar snap peas are delicious. And your trolley starts here. Oh, let's get a pen. So your trolley starts here. Although actually I've been avoiding supermarkets recently and trying to get all my food from farmers markets, which has been tough, but I'm doing pretty well so far. Anyway, you push in your trolley towards the peas, and so you push them in that direction. You push your trolley in this direction. Now, this is a vector, and the way we describe vectors is we look at how far they go across and how far they go upwards. So this vector, let's say it goes 5 across and 3 upwards, then we would call this vector 5, 3. Now, can anyone tell me how long this pink line is? How long is the pink line going to be if it's going 5 across and 3 up? What do we think? How long is this vector going to be? So t is saying 2. Now, it's not going to be 2, is it? Because if you look at the length of this pink line here, let me just double it up again, it looks kind of longer than 5, and it's definitely longer than 3. So we need something that combines the 3 and the 5. So if you haven't done this yet before, I'll just do a really quick recap. So Pythagoras' theorem, this is a theorem come up by this amazing ancient Greek mathematician who figured out loads of this cool... this is something figured out by this ancient Greek mathematician who figured out this really cool relationship to show that if you take any right-angled triangle and you label the sides A, B, and the longest side C, so that's the side opposite the right angle, then A squared plus B squared equals C squared. And it's one of the most important relationships in the whole of maths. And it's like, without this relationship, loads of the most amazing buildings that have ever been built throughout history would just never have stood up, because builders just could not have calculated how to make things work without this relationship. It's so important. So if we do 5 squared, then that's going to be 25, plus 3 squared is going to be 9, equals C squared. So we need to do 25 plus 9. It's going to give us 34, and then we need to square root that. So C, this length, is going to be the square root of 34, which I've seen answers coming up to say 5.83, which is something you really like. Do that on a calculator. Don't try and do the square root of 34 without a calculator. I mean, you can if you want, but you'll be there for some time because it's hard. So yes, you can find the length of a vector by using Pythagoras' theorem, and we're going to practice that again later on. But first, I just wanted to show you what a vector is and how we draw it. So, so see if you can just visualize before I draw it. How would you draw this vector? If we had the vector -3 and 2, then what would that look like? What would that look like? So if we're starting here, then -3 is what we do first, and that's what we do to go across. So think of it as being, think of like a graph. On a normal graph, you always go across first, that's your x, and then you go up and down, that's your y. So we go across first, and then we go up and down, and it's the same for vectors. So if we've got -3, 2, then that means we're going to go -3 in the x direction. So that means -3 to the left. Oops, wrong thing. So we'll go -3. So that means to the left, because it's minus. And then 2 up. So 2 up. So the vector -3, 2 is just a line that goes in this direction. It starts here and it goes to here. Now, could anyone tell me how long that vector is? How long is the vector -3, 2? What is its length? Now, again, throw your answer into the chat if you can do it faster than me, but I'm just going to go through it as an explanation quickly. So again, let's use this same triangle. So the length here is -3, so we're going to do -3 squared plus 2 squared, because that's the length here, and that's going to give us our answer squared. So -3 squared is 9, because -3 times -3 is 3 times 3 is 9, and minus times minus is plus. So that's going to be 9 plus, and then 2 squared is going to be 4, and that's going to equal our answer squared. So we're going to be needing to do the square root of 13, because 9 plus 4 is 13. So 13 is c squared. So our answer is going to be the square root of 13, which is going to be 3.6. Perfect. Good. So the answer to this length is 3.6. Okay, cool. So that's what a vector is. A vector is just a line going in a certain direction, and we label it by saying how far across it goes and how far up or down it goes. Now, let's do the next bit and go across to here and look at multiplying vectors. Oh. So let's go here. Let's just get rid of this bit. Okay, so now how do we multiply vectors? So let's say we've got another vector, and let's label out another one. So this one can be going, so let's say we're going to start here, and this vector is going to go like this. It's going to go down here, like that. So this vector we would label with how far down it goes. So let's say it's going down by 4, and then let's say it's going across by 5. So this is -4 because it's going down by 4, and then -5 because we're going across by 5. Now, I've done this in what might be a slightly confusing order, because we always talk about going across first and then going down. So we'd label this vector as -5, -4. Just let's stop a moment and make sure that makes sense to everyone. So it's -5 because in the x direction we go -5, so 5 to the left, and then in the y direction we go 4 down. So first we go across by 5, and then we go down by 4. So that's why we call this vector -5, -4. Now, if I told you that I wanted you to take this vector and times it by 2, then in terms of the arrow, it's really easy to see what it's going to be. The vector is going to be exactly the same as it was before, but instead of being this long, it's going to be doubly as long. So now our new vector is going to be this long, because it's doubly as long as it was before. And also, it's probably quite easy to see that instead of going 4 down, it's now going to go, what do you think? How far down are we going to go now, and how far across are we going to go now? And therefore, what is our new vector going to be? So because we were going down -4 before, now because we're doing double that, because we've doubled the length, we're going to be going down -8, and we're going to be going across minus 10. And Miz is spot on with saying that we're going to go 10 across first and then 8 down. So well done for not falling into the trap. So yes, the new vector is going to be minus 10 minus 8. Now notice how this is literally as simple as taking the first vector and just timesing it by 2. 2 times minus 5 is minus 10. 2 times minus 4 is minus 8. So let's see if everyone can do this. I'll just give you one test of that idea. So if we've got a vector which is 3 minus 7, and I want you to times it by 2, then what does that give us? Karina, spot on as well. Perfect. So if we take this vector and we want to double it in size, then it will become, brilliant, 6 and minus 14. Perfect. So that means it's going to go, just to keep recapping what vectors means, it means we're going to go 6 across and, shouldn't have done that so low, 6 across and 14 down is what this vector means, which means this vector is going to look something like that. 6 and minus 14. Really nice. Okay, cool. Now let's do the next bit. So I'm just going to we'll get up here. Going to get rid of that high-speed ant. Although for those joining late who missed that fact, that's such a cool fact that the Saharan silver ant can run at about 85.5 centimeters every single second, which is basically like the equivalent speed of a human if we scaled it up, running over 100 meters every second, which is crazy. Anyway, okay, so adding vectors. So this bit is where it starts to get a bit more interesting. So let's say we have, let's take 2 vectors. I'm going to do an orange one, and that orange one I think is about 1 across and 3 up. So let's call it 1, 3. And this blue vector, we'll do like this. And this blue vector, I reckon, is maybe about 5 across and 2 up. So here, let's just quickly recap to make sure that makes sense. This vector is 1, 3 because we go 1 across and then 3 up. In comparison, this 5, 2, we're going 5 across and then 2 up. 5 across and 2 up. Now, if we add these together, it's like the equivalent of just writing one after the other. And your answer is going to look like this. Starting in the same position, but finishing here. Now, to start in the same position and finish there, we're going to need to go 1 across and also 5 across. So in total, we're going to go 6 across. And we're going to want to go 3 up and then 2 up. And so we're going to be going 5 up. So the new vector is 6, 5. So let's write this out up here to make it more clear. If you're doing vector 1, 3, and you're adding the vector 5, 2, then the answer is just 1 plus 5 is 6, and 3 plus 2 is 5. So have a go at doing one by yourselves to make sure this makes sense. So what would happen if we take these vectors and add them together? So if we took 3 and minus 5, and we added it to 9 and 3. What would that give us? Now, to visualize this, I really want you to be thinking, okay, so 3 across, 3 across, and then 5 down is going to look something like this maybe to begin with. So that is going to be our 3 across and 5 down. And then 9, 3 means we're going to go, means we're going to go something more like 9 across and then 3 up. So it might look something like that. And so in total, the answer is going to be 12 and minus 2. Perfect, you've all got that right. Really good. So 12 and minus 2, which is, you can see quite simply, 3 plus 9 is 12, and then minus 5 add 3 is minus 2. But look at how beautifully it works visually. Like if you start at this point and you finish at this point, then that looks a lot like, because it is, you're going 12 across and 2 down. So 12 and 2. Now, what about if you minus vectors? What do you think happens there? Let me get rid of this. So if I gave you this one, let's do it in brown. So if I gave you 5 minus 7 minus 3 minus 4, then what vector would we get there? What do you think? I'll give you a moment to work it out. And just to make it visual, I'll just do that over here. So 5 minus 7 would be like starting here and going 5 across and then 7 down, so something like that. And then if we were to go 3 across and 4 down, and that's actually the opposite of what's happening here, because we're minusing 3 across. So we're going the opposite of 3 positively across, and then we're going the opposite of 4 down. So we're going to end up somewhere around here. So actually the vector we're looking for in the end is going to be quite a bit smaller. So what do we think? So Miz is saying 2 and minus 3, so let's check that. So 5 minus 3 is 2, and then minus 7 minus minus 4 is going to be minus 3, which Karina got as well. Perfect. Good. Okay, right, that's adding and minusing vectors. Now let's move on to some vector problems. So the thing about vectors is that I think that it's something that, as I said at the beginning, like loads of students come to me and ask me about vectors and say they're really stuck on them. I think vectors is something that's really just about learning a new bit of language, and the maths involved, as you've seen, can be quite easy. Sometimes it's just like adding and minusing and doing a bit of timesing. The problems are the things where it can start to get tricky. So let's have a go at a problem, which I'll just bring up over here. Here we go. So this here is a classic vector problem. Let me just get rid of this bit, we don't need that. Also, I might just grab this because this is what we're going to do now. Okay, so in this one, we have got labelled this hexagon, and it's a regular hexagon just made up of triangles, and it's been labelled up with all these letters, A, B, C, D, E, F, and so on. Now, to begin with, I've just shown you vectors as being like this. So something like 3, 4, to just mean it goes 3 across and 4 up. However, when you start to symbolize vectors, they're given in 2 different ways. They're either given, if you're looking at a diagram, as a journey from one place to another. So this is a journey from A to B, and notice how there's an arrow on the top to make it very clear that you're going from A to B. So from A to B is that journey there. Now we've got another journey labelled here, which is from 0 to A, so O to A. Now O to A has already been labelled for us with a piece of algebra, which is X. Now normally you'll see algebra that represents vectors in bold. So it's normally written in bold, and where it can't be written in bold, it'll be underlined. So let's underline both of these to show that they're definitely vectors. So X is a vector going from 0 to A, Y is a vector going from 0 to B. So if you want to find out the vector going from A to B in terms of algebra, then you have to ask yourself, what is the journey to get from A to B? How do we get there? But how do we get there using vectors that we already know? Now, does anyone already know the answer to this? I'm interested to know if this is something that people already know or whether this is new to people. But I will now walk you through how this problem works. So to get from A to B, we don't have to go directly from A to B. We can actually take any route we want around the shape and we will still get the same vector answer. So we can literally go any route that we want. Now, the easiest route to go is going to be this one. Going from here down this way and then up this way. And the reason why is because we know what this vector is and we know what this vector is. And so we can combine them in a total journey to get from A to B. So if we start at A, then to get to this middle point here, we don't want to do X, but we actually want to do minus X because we're doing X backwards. So to get from here to here, we do minus x, and remember to underline it because it's a vector. And then we're going to go from here to here, and so to do that, we just add y. So a to b is just minus x, add y, or y minus x. So yeah, a to b is y minus x. So I can see, Karina, that you've put x plus y, so I wonder if that's affected your other answers. Let me just rearrange that there, let's make it a bit clearer. So a to b is y minus x. Now, when you're solving these kind of problems, it's often good to like keep written down a whole library of the ones you figured out before, because you can use them again. So notice how this vector from a to b, I just want to label it with a red line here. Notice how this vector from a to b here, which we know is just y minus x. So we know that this line here is just the direction is y minus x. Notice how that's exactly the same as the vector from f to o. It's the same from o to c. It's the same from e to d. So we can use this one again, and it's going to be really useful for helping us to figure out something else. So if we want to do f to b, then the route that we can take is like this. We can go from f, and we can go up here, which you can see is just the same as y. So this is just y again. And then we can go along this route, which we know is y minus x. So if we're going to do y, and then we're going to do add y minus x, then the answer for FB is going to be 2y minus x. Which, Karina, I can see you got that one spot on. Perfect. So FB is 2y minus x. Now FD is now a similar journey that we can do by thinking the same way. So to get from F to D, if we start here and we're heading in this direction, then from F to O we know is the same as this one because it's the same direction. So we're going to do, so that's going to be y minus x. And then to get from here down to here, this here is exactly the same as x, but backwards. So we're going to be minusing another x. So it's going to be y minus x, which is going to give us y minus 2x. Perfect. Okay, great. Right. So now that was one of the kinds of problems that you might get with vectors, where you just kind of have to add and minus them and look at the shape to try and figure out how to navigate around it. Now I want to finish on one of the like a really hard vector problem. So this is basically as hard as they get. Kind of ages, as I said, like generally about age up to age kind of 16, 17, you won't get anything much harder than this. So here we go. Here is a parallelogram. So it's a parallelogram, so we know that this side is the same as this side, and we know that this side is the same as this side. Now, this parallelogram has been labelled up with 0 as the starting point, and then x, y, and z as the corners of this parallelogram. Now, I've also labelled M, and M is the midpoint, so it's the halfway point from x to y. M is the midpoint from x to y. And then N is just what you get when these two lines cross. So this is the line going between z and x, and this is the line going from 0 to the midpoint. So N is a kind of mysterious one that we'll look at later. Now, if you also know that going from 0 to x is 8 across and nothing upwards, then we can label the vector like that. And if you know that going from 0 to z is minus 2, so 2 to the left and then 6 up, then we can label it in this way. Right, now, who can figure out, let's do these one by one. Who can figure out what x to m is? How do we write x to m? So how do we go from x to m? So have a go. I'm going to walk you through it again, but like if you feel that you can do this faster, then throw in the answers, and we will. And yeah, in fact, Karina's already got it, which is great. So if you look x to y, is remarkably similar, well, it's identical because it's a parallelogram, to this line. So this line here, let me just grab it. So this line here is 0 to z, and it's exactly the same as x to y. It's the same line. So, because this is the same line, that means that if we go from x to m, then that's halfway from x to y, so it's going to be exactly half of this. So Kareem's spot on with saying it's -1, 3. Perfect. Oops, let's just make that clear that it's -1 on the top. So 1 to the left and 3 up. Great. Okay, now that's really good. Now, can we figure out what x to z is? How do we get from x to z? Now to do this, we're going to start our journey here, and we want to finish it here. So a good route that we can take is we can go from x to 0, so that's going to be the opposite of this vector, and then we can go from 0 to z, which is going to be the same as this vector. So to work out this one, I'm just going to move that up a little bit. So to work out this one, so we're going from x to 0, so that's going to be -8, because we're going backwards, and 0. And then going from 0 to z, we're going to be adding that one, so that's going to be, because we're going in the same direction as it. To get this, notice how, look, this one I've made negative, because we're going backwards down this vector to get from x to 0. But this one here, I've made positive. We're just adding that one as normal because we're going from 0 to z. And that's how we do our full journey that takes us all the way from x to z via 0. So in total, x to z is going to be -10 and 6. Perfect. Well done, everyone. That's so good. Okay, great. Now, here comes the challenge. How do we do 0 to n? And this is by far the hardest question that I'm asking here, but I'm kind of interested to know how much this has helped people and how much this made sense. So I'm going to go through this, and this may seem slightly mad. And this is, as I said, like by far the hardest problem that you ever get in vectors. Up to age 16 normally, unless you're in a school that's kind of really accelerating forwards with vectors for some reason. But this is generally as hard as it gets. So to get from 0 to n, we need to think of the journey. So to get from 0 to n, it's like we're going from 0 to m, but we're only going part of the way. So what I'm going to say is that we're going, I'm going to use the letter Q. So we're going Q of the way from 0 to m. And what I mean by that is that Q might be something like 70%, like maybe it's 70% of the way to m. So Q might be 0.7. So O to n is the same as a fraction of O to m. So it's going to be Q, and then O to m is going to be the same as 0 to x, and then x to m. So we know 0 to x is 8, 0, and we know x to m is -1, 3. So let's just do this over here. So we're just finding O to m at the moment, so it's going to be 8, 0 to go from O to x. And then what else? What do you guys think? So x to m, we're then going to do -1, 3. So let's go from O to x and then x to m. In total, it's going to be 7 and then 3. Exactly, only halfway. That's right. So I can see why you got confused, because we're only going to the midpoint here. And look, remember, we've stored that information in our library. X to m we've got over here. It's -1 to 3. -1, 3. So overall, that is Q of 7, 3. Now, that isn't enough to work out O to n because we don't know what Q is. But there's another way of doing it. Because we can also work it out slightly differently. So we can also work it out by taking a different route. So we can go from O to n by going via x and then going this way instead. So if we do that, then we can say that O to n is also, let's write it over here. So O to n can also be written as going from O to x and then x to n in this direction. So we go from here to here and then to here. So what does that whole route look like? So O to x is going to be 8, 0. And then we know that x to z is this because we've written it here. So now let's say we're going a fraction of the way across. So instead of using q, let's use a different letter. Let's use p. So now we're going to go p of the way from x to z. So it's going to be p of minus 10, 6. So this is probably seeming quite mad if this is your early days in vectors, but I wanted to do a really hard problem to see if anyone could solve this one. I'm especially interested in if Karina can solve this one because Karina's been so good at all the other ones. Right, we're going to need a bit more space, so I'm just going to move a load of this bit upwards. I'll just pop it up there. So now we have a situation where we know that ON is this, and we know that ON is also this. So therefore, these things are equal to one another. So we can write this out. So we can write Q of 7, 3. So that's this bit here, equals 8, 0 plus P of minus 10, 6. Now, here's the magic thing about vectors that I wanted to introduce you as a last concept that I want to cover, which is that if you just take the top line, then you can form one single equation with the top line. And you can also form another equation with the bottom line. So if we take the top line, then we can see that it's 7 equals 8 plus p times minus 10. So in other words, let me write it over here. 7 equals 8, and then plus p times minus 10 is the same as minus 10p. Oh, sorry, I missed a bit. Sorry, it's q times 7 at the front. 7 times q equals 8 plus p times minus 10. So it's 7q like that. 7q equals 8 minus 10p. So that's the top line. And what the bottom line gives us is 3 times q. 3 times q equals 0, so we can ignore that bit, plus 6p. So 3q equals 6p. Now, what you have here are a pair of simultaneous equations, which we were doing the other day. So these two equations are both true. And because they're both true, you can solve them to find the answers. So what I'm going to do now is just delete all of this stuff because we can save a bit of space here. I'll really quickly recap this. So the top line is q times 7 equals 8 plus p times minus 10. And the bottom line is q times 3 equals 0 plus p times 6. And that's where we've got these equations from here. So let's get rid of this to make ourselves a bit more space because we don't really need that anymore. And we can get rid of this too because we're not going to need that again. So there we go. These are the simultaneous equations that we're trying to solve. And we're trying to solve them because we know that ON is equal to Q of 7 over 3. So now let's quickly try and solve these equations. So what I would do first is I would take 3q equals 6p and I'd divide it all through by 3. So if you divide both sides by 3, then you'll get q equals 2p. And this means that you can now sub this information into the first equation. So who can write out what that's going to be when we sub this into the next equation? What will we get? And we take this and we sub it into that one. What do you think? So I'm going to start subbing this in. So we had before 7q equals 8 minus 10p. 7 cubed. Instead of q, we know that q is the same as 2p. So let's write that instead. So that means that, yes, perfect. M. Chiro, that's brilliant. So 14p equals 8 minus 10p. Cool. And so then we can add 10p to both sides to get 24p equals 8, which means that p equals what? What does p equal and what does q equal? Can you guys do the last step? What does p equal and what does q equal? Perfect. Karina, that's spot on. So p is a third because 8 divided by 24. And that means that q is going to be what? Q is 2 times p. So q is going to be... Come on, Miz, I know you can do this. Oh, Karina's got it. Great. So q is going to be 2/3. Perfect. So p is a third and q is 2/3. Nice. Now, if q is 2/3, then that means that we can go back to our original problem and say that if q is 2/3, then we need to take 2/3 of both of these. So 2/3 of 3 is just going to be 2, and 2/3 of 7 is a bit more complicated. It's going to be 14 over 3, which we'll get as a decimal. What's that decimal going to be? Let's just call it 4.7. So there you go. ON is 4.7 and 2. And that is the end. So there you go. That was a really hard vector question, which I just wanted to do to kind of consolidate everything and bring it all together, and also give a challenge to those who were finding the earlier vector stuff easy. But yeah, so I hope you all found that interesting. As I've been saying on other lives, if you would like to, if you're keen to be interviewed by us, because we really want to learn more about how people are finding this, do email team@aimhigh.co telling us that you're up for chatting to us, because we would love to chat to some of our students and learners to figure out how we can make this better. If you're up for it, please email that. Otherwise, thanks so much for coming along. Do subscribe to get our schedule there if you haven't already. Follow our socials here and do tell your friends. I will be back tomorrow with 2 more lessons. Hannah's going to be back. Josh is going to be back. There's going to be more biology, more chemistry to come back. And thank you so much for coming along. And Miz is right. Karina, you are such a maths genius. Great job. So I will see you all tomorrow. Farewell. Bye bye.